Coulombs law is the force law that determines the magnitude and direction of the force between two charged particles. So we have a formula here on the left, which is a vector formula, so it indicates a magnitude and a direction for this force. And here's what it says. First of all, you have charges Q1 and Q2 in the numerator here. So this tells us that the force is proportional to the product of the two charges. That means if I double the magnitude of either charge, I would double the amount of force. The force is inversely proportional to the square of the distance between the charges. So here we have R12. R12 literally just is the distance between these two charges. So that means that if I double the distance between the charges, the force will be divided by a factor of 4. There is this prefactor, 1 divided by 4 pi epsilon 0, and you could think of that as a proportionality constant. So we're saying the force is proportional to the product of the two charges. It's inversely proportional to the square of the distance. 1 over 4 pi epsilon 0, that ratio is really just the constant of proportionality that sets the scale of the force relative to your system of units. Epsilon 0 is called the permittivity of free space, and the ratio 1 over 4 pi epsilon 0 is called Coulomb's constant. And I'll give you the specific value for those in a little bit. R12 hat is a unit vector. Remember, hat means unit vector, a vector of magnitude 1, so it just is kind of neutral in terms of its size. And this is the direction part of the force. And what this little unit vector represents is the direction that points from charge 1 towards charge 2. So Coulomb's law basically says the force is parallel to the line connecting the two charges, and it's either going to point in such a way to make them be attracted to each other, or it's going to point in such a way to make them repel each other. So in this case, if both charges are positive or both charges are negative, the force that Q1 exerts on Q2 will try to push Q2 away from Q1 along the line connecting the two charges. If they had opposite signs, then the negative would reverse the direction of the vector, and then it would be an attractive force that tries to push charge 2 towards charge 1. Okay. We have some formulas here, and these formulas are to help you compute R12 and R12 hat. So R12 is just the distance between the two charges. So we have two order pairs here, x1 and x2, x1 and y1, and x2 and y2. And R12 can be computed just using the standard distance formula. So that's the formula for computing the distance between those two charges based on their coordinates. R12 hat is a unit vector, and it's formed by taking the vector, the displacement vector from charge 1 to charge 2, and dividing it by its magnitude, which is the distance connecting them. So if I have charge 1 here, and I have charge 2, the displacement vector, R12, would be the vector which points all the way from charge 1 to charge 2. This vector is formed by essentially taking the difference in the x-coordinate and the difference in the y-coordinate in each coordinate direction. And then we divide that vector by its magnitude, which is the distance between them, which gives us a unit vector for R12 hat, a vector with a magnitude of 1. So now I need to deliver on telling you the values of the epsilon 0 constant and Coulomb's constant. So here we have the permittivity of free space right here, and that is epsilon 0. And epsilon 0 is equal to 8.854,187,817 times 10 to the negative 12 Coulomb squared per Newton meter squared. This is an exact value as defined by the current system of units. So, and essentially what this does is this sets the scale for how we measure charges relative to forces. It's called the permittivity of free space, and that essentially means the permittivity of the vacuum. So this is essentially the strength of how the electrical force that a charge exerts on another is moderated by the presence of the medium they're in this case the vacuum. If the two charges were, say, in a solution, like water or some other material, then the presence of that material would have an effect on how much force they could exert on each other. And so in those situations, the permittivity would depend on the properties of the material. So you'll see things like the permittivity of water or the permittivity of crystal and other various materials. Sometimes permittivity is referred to as the dielectric constant of a material. And essentially the only effect it would have, practically speaking, for computing forces would be that the material would simply change the value used for epsilon. So it would be epsilon instead of epsilon 0. Coulomb's constant is the ratio 1 over 4 pi epsilon, and that is 8.987551788 times 10 to the 9th Newton meter squared per Coulomb squared. This is exact because epsilon 0 is exact. So what that means is this isn't something determined by experiment, but rather it's just a definition of the units that we work with. And Coulomb's constant is probably the one that's more practical to memorize in the short term, because whenever you do a force calculation, you're just going to want to know what that ratio is that's in front of the Q1 times Q2 over R12 squared. And so you might notice that the first three digits here round to 8.99, and so we're usually going to just round that to either just 8.99 times 10 to the 9th, or even for particularly crude calculations, we'll just say 9 times 10 to the 9th. Okay. Similarly, when we work with the permittivity of free space, epsilon 0, we'll just use the first three digits for most calculations, 8.85. And if the calculation is particularly crude and we don't care about the exact value, we might just round that whole thing to 9. So now we'll do our first Coulomb's law example. And this is to determine the magnitude of the force between a positively charged 3 microcoulomb charge and a negatively charged 2 microcoulomb charge, which have a distance between them of 15 centimeters. And we are going to start by writing the relevant knowns and unknowns and the equations that relate them. So in this case, the equation is pretty obvious. The magnitude of the force is 1 over 4 pi epsilon 0 times the ratio of the product of the two charges to the distance between the charges squared. My knowns are the charges and the distance. Charge 1 is positive 3 microcoulombs. Charge 2 is negative 2 microcoulombs. And the distance is 15 centimeters. My unknowns, well, I really only just have one, and that's the force. That is not known. I also do know that 1 over 4 pi epsilon 0 is approximately 9 times 10 to the 9th newtons meter squared per Coulomb squared. And the reason I'm rounding that to only one significant digit is because our charges here only have one significant digit anyway, so there's no point in wasting effort with more significant digits in Coulomb's constant if the rest of my data isn't that precise anyway. Okay. So in this case, it's pretty easy to figure out the force. You just plug in these values because our equation for Coulomb's law relates the force to the known values. So now we'll go ahead and do that. So the force is going to equal, okay, first I'm going to have Coulomb's constant. So actually let me just rewrite the equation with variables here. Okay. So first let's just put on Coulomb's constant. So that's going to be 9 times 10 to the 9th Newton meter squared per Coulomb squared. Then we're going to have the two charges. And we're going to have the distance between them squared. So let's review. What were the two charges? Positive 3 microcoulombs and negative 2 microcoulombs. So we have positive 3 microcoulombs and negative 2 microcoulombs. The distance was 15 centimeters, so I'll put 15 cm. Now before I start doing arithmetic, I need to handle the SI prefixes. In this case, I've got micro here, which is 10 to the negative 6, and I have centi, which is 10 to the negative 2. So I need to think of that 3 microcoulombs as 3 times 10 to the negative 6 coulombs. Okay. So we'll proceed. So first of all, as far as significant numbers are concerned, we'll have 9 times 3 times 2. So 9 times 3 will be 27, and then 27 times 2 will be 54. And one of those three factors in the product is negative. Then we have to deal with the orders of magnitude. We have 10 to the 9, 10 to the negative 6, 10 to the negative 6. So this will be an order of magnitude that will be 10 to the 9 minus 6 minus 6. 9 minus 6 is 3. Subtract another 6 is negative 3. Okay. As far as the units are concerned for the top, I have Newton meter squared per Coulomb squared times coulombs. And the result is that these coulombs cancel that Coulomb squared in the bottom. Now I have to deal with the denominator. The denominator has a 15 squared and a 10 to the negative 2 squared. The 10 to the negative 2 squared will just become 10 to the negative 4. And then 15 squared will be 225. So I have 225 in the bottom and 54 upstairs. The results, or the units of the bottom, will have meter squared, because it's a meter times a meter, or it's just the distance squared. That meter squared will cancel the meter squared in the top, so now the units are just newtons. So I am now in a position to finish the arithmetic. We have negative 54 over 225 times 10 to the negative 3 over 10 to the negative 4. The 10 to the negative 3 over the 10 to the negative 4 is just going to become 10 to the first. And then I have to figure out what 54 over 225 will be. So to do that, I need to get a calculator. and it looks like that ratio is 0.24. So I now have negative 0.24 times 10 to the first newtons. Now, of course, I just care about the magnitude of the force, so the sign doesn't really apply in this case. So I really should have put all of these in absolute value bars from the beginning. And so this will be 0.2, or let me rephrase that. This will be 2.4 once I take into account the 10, 2.4 newtons. Now, as I said at the beginning, many of my factors only have one significant digit, so that 0.4 can be discarded as non-significant. So really the force, when I take significant digits into account, is 2. So it could be anywhere from 1 newton to 3 newtons because we were so imprecise in the measurements. But anyway, that is the math, and that's how you would work out the magnitude of the force in this case. Okay, our second example. In this case, this is a problem of determining the direction of the net force on charge 3, where charge 3 is one of 3 charges in an equilateral triangle, as indicated here. And we know that charge 3 has a positive charge, a multiple of some charge called Q. Charge 1 has a charge Q, and charge 2 has a charge negative Q. And so in this case, I want to know just the direction of the net force. So we have F net, and we want to know which way does it point. Is it going to point upwards, to the left, to the right, or is it going to point down? To solve this, we need to think about the direction of the forces as indicated by Coulombs law. So remember, Coulombs law is proportional to r hat, right? Where r hat is a vector which points along the direction of the line connecting the 2 charges. So if I look at F13, regardless of what happens, it is going to point in R13 hat direction, right? It's going to be parallel to this line. Now, charge 1 is positively charged, and charge 3 is positively charged. So I know that the force that charge 1 exerts on charge 3 will be a force that will tend to repel 3 from charge 1, which means it's going to point this way. Okay. Next, and so this is F13, the force that charge 1 exerts on charge 3. Next, we have the force that charge 2 exerts on charge 3. That force is once again going to be directed along the line connecting charge 3 and charge 2, which is this line right here. But in this case, charge 2 is negatively charged. And so the force that charge 2 exerts on charge 3 will be an attractive force. This will try to pull charge 3 towards charge 2. Next, I got to think about the sizes of these arrows. So I have the force that charge 2 exerts on charge 3, and I have the force that charge 1 exerts on charge 3. And I've drawn the arrows to try and indicate that they're roughly the same length. How do I know that? Well, I know they're the same length because the magnitude of charge 1 is the same as the magnitude of charge 2. So if I compare, let me write the full Coulombs law here. If I compare my magnitudes, the magnitude that charge 1 exerts on charge 3 is going to be Coulombs constant, charge 1, charge 3, over the distance from 1 to 3 squared. the magnitude of the force that charge 2 exerts on charge 3 is going to be Coulombs constant, charge 2, charge 3, divided by the distance between 2 and 3 squared. Well, and of course I'm only caring about absolute value here. So, for the force that 1 exerts on 3, I would have K, positive Q, 16Q, divided by A squared. For the force that 2 exerts on 3, I would have K, positive Q, 16Q over A squared. Remember, charge 2 had a charge of negative Q, but because of the absolute value bars, that negative sign goes away. So these are identical, and therefore the magnitude of those forces is the same. So now I have these two forces, F1 on 3 and F2 on 3, one of which points up and to the right and the other which points down and to the right. So now I need to add these forces. And so I'm going to create a little free body diagram. And I'm going to draw the forces. So here is F1 on 3. Here is F2 on 3. Now I'm going to add the forces tail to tip. So to add the forces tail to tip, you follow one force and then the next. So first I'll follow F of 1 on 3. There's my F1 3. Then I'll follow the F2 on 3. That's this guy here. And what I get is a force which results in pointing to the right. So my resulting force, or my net force, is right here. And I know that it points directly to the right because the angles that these forces make are such that their vertical components are equal and opposite. So to convince you of that, I need to go work out the angles. Alright, so I need to work out the angles on this triangle, so I can get the angles that these force vectors make. This is an equilateral triangle, so we should know from trigonometry class that each of those angles are 60 degrees. Now, if I cut this top corner with a horizontal line, then I can use geometry to figure out these angles here at the top. So for instance, this angle. This angle will be 60 degrees because that same line, when cut by a horizontal line, makes a 60-degree angle down here. So this is a 60-degree angle. Now I'll go ahead and indicate that in the free body diagram. This is 60 degrees. Next, if I label this angle as theta, then I know that 60 plus theta plus 60 had better equal 180 degrees because these three angles are supplementary to each other, right? They form a line. So that means theta is 180 degrees minus 120 degrees, which is once again just 60 degrees. Going over here, that makes this 60 degrees. So this is 60 degree. This is a 60 degree angle. This is a 60 degree angle. The vectors have the same magnitude, and therefore these vertical components will just cancel. So the direction of the net force that was requested is now known. It points to the right. Okay, we are now going to do example 3, which is to determine the magnitude and direction of the force exerted on charge 3, which is indicated here in the picture. Charge 3 is at a corner of a right triangle, which has side lengths of 3 centimeters and 4 centimeters. And at each corner of this triangle, there is a charge. So charge 1 is at the bottom left here. It's positively charged with a charge of 3 nanocoulombs. And charge 2 is at the bottom right with a charge of negative 5 nanocoulombs. First thing you should always do in this type of situation is set up a coordinate system. So I am going to identify the bottom edge of this triangle with the x-axis and the top, not the top, but the vertical facing side with the y-axis. And so we now have a coordinate system. And now we have coordinates for each of these charges. So Q3 is at the coordinate 0, 3 centimeters. Charge 2 is at 4 centimeters, 0. And charge 1 is at 0, 0. Okay. So I've identified coordinates. And now I'm going to make my list of knowns, unknowns, and equations. So in terms of equations, which are usually the most fruitful place to start, I know how to compute the force that one charge exerts on another. So to avoid confusion with these subscripts, I'm just going to write A and B as the labels for the charges. And I know the electrostatic force that charge A exerts on charge B is going to be 1 over 4 pi epsilon 0, charge A, charge B, over the distance from A to B squared, times the unit vector that points from A towards B. Okay. The magnitude of this force is just 1 over 4 pi epsilon 0 times the absolute value of QA, QB over the distance from A to B squared. Okay. Now I have my knowns and unknowns that I need to work out. So, what are my knowns? Well, I know that charge 1 is 3 nanocoulombs. And I know its coordinates. The ordered pair is 0, 0. I know that charge 2 is negative 5 nanocoulombs with an ordered pair of 4 centimeters, 0 centimeters. And charge 3 is positive 2 nanocoulombs with an ordered pair of 0, 3 centimeters. So I know what all the charges are and where they're located. Okay. What are my unknowns? Well, just draw some dividing lines here. So my unknowns include the distance from charge 1 to charge 3. It might be kind of obvious to you looking at the triangle, but technically that's an unknown. The distance from charge 2 to charge 3. The unit vector from that points from charge 1 towards charge 3. The unit vector which points from charge 2 to charge 3. Force that charge 1 exerts on charge 3. And the force that charge 2 exerts on charge 3. And of course, I want to know the net force ultimately. And so all of these are unknowns. The unknowns suggest to me a few equations that I may have forgotten, so I'm going to write those in here. So first of all, the distance from A to B is the square root of the difference in the x-coordinates squared plus the difference in the y-coordinates squared. Okay. R hat AB is going to be the difference in the x coordinates times I hat plus the difference in the y coordinates times j hat, all divided by RAB. And the net force is going to be the force that charge 1 exerts on charge 3 plus the force that charge 2 exerts on charge 3. So now that I have everything mapped out, it's simply a matter of my personal choice in terms of how do I want to start working out these unknowns and getting specific numbers for them. So before I do anything, it's really convenient to start working out distances. So I'm going to start by working out R13 and R23. So for R13, this is relatively easy because if you go back on the previous page, you can see pretty clearly that this side of the triangle is the distance from charge 1 to charge 3. That should be pretty obvious. You can use the formula and you will get that answer, but we'll just say, okay, that is 3 centimeters. Distance from charge 2 to charge 3, I have to work out using the Pythagorean theorem. You might recognize that this is a 3, 4, 5 triangle, so that we just know that this is going to be 5 centimeters. But I'm going to use the Pythagorean theorem to solve it regardless. So, the distance from charge 2 to charge 3 is going to be the square root of the difference in their x-coordinates squared plus the difference in their y-coordinates squared. What are these differences? Well, charge 3 has an x-coordinate of 0 centimeters, and charge 2 has an x-coordinate of 4 centimeters. So this will be 0 centimeters minus 4 centimeters. Now charge 3 has an x-coordinate of y-coordinate of 3 centimeters, and charge 2 has a y-coordinate of 0 meters. So if I go to the y-coordinates, I'll get 3 centimeters minus 0 centimeters. Now I evaluate those differences and I get 4 centimeters squared plus 3 centimeters squared. This is the square root of 16 square centimeters plus 9 square centimeters. 16 and 9 make 25 square centimeters, which works out to 5 centimeters after we compute the square root. So 2 of our unknowns are now known. This is 3 centimeters, and this is 5 centimeters. Next, we'll go to R13 hat and R23 hat. So R13 hat is delta x I hat plus delta y j hat, all divided by R13, the distance. Now the delta x actually does matter here, that it is the final destination minus the origin, not the other way around. We didn't have to worry about that when we were doing the distance calculations because the difference was squared, and that makes the order of the subtraction irrelevant. But for the unit vector, the order of the subtraction really matters. And so sometimes you're going to get this backwards, and so you got to just kind of think through it logically to make sure that you're doing the right thing. Now this one is in fact one that you should be able to just do in your head looking at the picture, but we will work it out. So if I go back to the picture, I need the unit vector that points from charge 1 to charge 3, right? Well, that's just a vector that points directly upwards. So this would be R13 hat. And that should just be the same as the j hat vector, right? So remember the j hat vector is a vector that points just in the y direction. So R13 hat, it would just be j hat. But we'll see it in the math that when I do this difference, so what do I have? So I have x3. So the x-coordinate for q3 is 0. The x-coordinate for q1 is also 0. And now we'll add on the difference between their y's. So the y-coordinate for q3 is 3 centimeters. And the y-coordinate for q1 is 0. All of that is going to be divided by 3 centimeters. And now you can see that this is going to just go away because it's zeros. This can be ignored because it's subtracting a 0. And so what I end up with is 3 centimeters j hat divided by 3 centimeters. But of course that ratio just cancels to 1. So I just get a j hat as my answer, which is what we expected. So R13 hat is just j hat. Now we need to get R23 hat. This is once again going to be delta xi hat plus delta yj hat, all divided by R23. This will be x3 minus x2 I hat plus y3 minus y2 j hat, all divided by R23. Now plugging in the numbers, the x-coordinate for q3 is 0, the x-coordinate for q2 is 4 centimeters, the y-coordinate for q3 is 3 centimeters, the y-coordinate for q2 is 0. The distance between them is 5 centimeters. So now I get negative 4 fifths I hat plus 3 fifths j hat. And this is our unit vector. I won't go ahead and write it on the first page because it's going to be a little difficult to fit it in there. Yeah, so this is the vector that points from charge 2 to charge 3. So let's just kind of do a common sense check here. So the vector that I got was R2 hat, 23 hat, it's negative 4 fifths I hat, plus 3 fifths j hat. That means this is a vector which goes to the left, and it goes up, right? Because negative I hat would be a vector that points left, and 3 fifths j hat would be a vector that points up. So how do I get from Q2 to Q3? Well, I certainly do go left and then up. You see that? So you should always kind of just check and make sure that this vector is pointing roughly in the right direction that you expect. Even if you can't just tell by the numbers that it's pointing the exact correct direction at the right angle, you can still at least do a common sense check to see, like, okay, to get there I need to go up and to the left. Is my vector actually going up and to the left? Okay. All right. And we are finally in a position to start computing some forces. So now I can compute, for instance, the magnitude of the force that 1 exerts on 3. So this will be 1 over 4 pi epsilon 0. The absolute value of charge 1 times charge 3 divided by the distance from 1 to 3 squared. I know that 1 over 4 pi epsilon 0 is just Coulomb's constant, and that is going to be 9 times 10 to the 9th Newton meters squared per Coulomb squared. Charge 1 is going to be, let me just refresh my memory here. I think it was 5 nanocoulombs. Okay, no. So charge 1 is 3 nanocoulombs, and charge 3 is 2 nanocoulombs. So I can have a 3 and a 2. Okay. So I'm going to have 3 nanocoulombs times 2 nanocoulombs, all divided by 3 centimeters squared. Since all the factors in this expression are positive, I don't really need to worry about the absolute value signs, so I will drop them on the next step. Okay, so let's look at this. So we have the nanos. Nano is 10 to the negative 9, right? And centi is 10 to the negative 2. So I need to remember that when I'm working this out, what those orders of magnitude are. So I'm going to have 9 times 10 to the 9th times 6, because 3 times 2 is 6, times 10 to the negative 9th times 10 to the negative 9th, all divided by 9, because 3 squared is 9, and 10 to the negative 4, because 10 to the negative 2 squared is 10 to the negative 4. Now I can see some things that will cancel. So for instance, this 10 to the 9 cancels that 10 to the negative 9, and this 9 cancels that 9. So I'm going to be left with a relatively straightforward expression. 6 times 10 to the negative 9 plus 4. Or 6 times 10 to the negative 5th newtons. Okay. That's a 9. Now we'll compute the magnitude that force 2 exerts on force 3. Or force, not force 2, force 3. We'll compute the magnitude of the force that charge 2 exerts on charge 3. So this will be 1 over 4 pi epsilon 0, absolute value of charge 2 times charge 3, divided by R23 squared. This is going to be 9 times 10 to the 9th Newton meters squared per Coulomb squared. Oh, and I guess I dropped the units on the previous problem. Those will be newtons, and the way this works out is that I have the Newton meter squared per Coulomb squared from Coulomb's constant, and then from here and here I get a Coulomb squared, and from the square of this I get a meter squared downstairs. So the meter squareds cancel and the Coulomb squareds cancel, which leaves newtons. Okay, so back to the force that 2 exerts on 3. I'll have the absolute value. The distance is 5 centimeters squared. The magnitude of the charges is what? So Q2 is negative 5 nanocoulombs, and Q3 is 2 nanocoulombs. So I'll just put 2 nanocoulombs times 5 nanocoulombs. Oops. I don't have to worry about the negative sign because the absolute value bars. And the order that I write them in doesn't really matter because multiplication is commutative. So, Q2 times Q3 is the same as Q3 times Q2, which is what I have here. Okay. All right, so next step. So I'm going to have 9 times 10 to the 9 times 10 times 10 to the negative 9 times 10 to the negative 9 divided by 25 times 10 to the negative 4 Newton meters squared per Coulomb squared times Coulomb squared over meter squared. Okay, so I kind of raced through this one compared to last time because I've already gone through a lot of these steps in detail. The 10 to the negative 4 comes from the centi. The 10 to the negative 9s come from the nanos. And the 10 comes from 2 times 5. I also put all the units out here where the Coulomb squared come from the numerator and the meter squared come from the denominator. Okay. So, going through this, the Coulomb squared cancels the Coulomb squared, the meter squared cancels the meter squared, leaving units of newtons. This 10 to the 9 cancels that 10 to the negative 9. So I got to work out 9 divided by 25. So I need a calculator. Oh, actually, I can just do that here. So 9 over 25. If I multiply the top and bottom of that by 4, I'll have the same fraction. And that's going to be 36 over 100. So this is 0.36. So I'm going to get 0.36. That's a 3 times 10 to the 1 minus 4 minus 9. 1 minus 4 is negative 3. Negative 3 minus 9 is negative 12. So this is 0.36 times 10 to the negative 12 newtons, or 3.6 times 10 to the negative 13 newtons. Okay, so now we have the force that 2 exerts on 3. And notice this is way smaller than the force that 1 exerted on 3. So if I go back, force that 1 exerts on 3 is like, ooh, did I make a mistake? Yes, I did. Okay, so the mistake I made was that this should have been a plus 4. And so when I do that, okay, so we'll just erase this real quick. Okay. So what happened? So if I go back, I have times 10 to the first power from this guy, plus 4, because this negative 4 was in the denominator, minus 9 from this guy. 1 plus 4 is 5, so this is going to be a 5. Minus 9 is negative 4, so I have 0.36 times 10 to the negative 4 newtons, which is 3.6 times 10 to the negative 5 newtons. Okay, so what just happened there was I saw that the order of magnitude was dramatically different. And that clued me in to go back and check and see if there was a good reason for it to be so different. Because sometimes you look at the original problem and you think, oh yeah, of course it is. But the thing is, charge 2 is only 5 centimeters as compared to charge 1, which is 3 centimeters. The magnitudes of the charges are about the same. So if I get an order of magnitude that's so drastically different, I must have made a mistake. So that's how I noticed that there was a mistake there, and it's good for you to kind of learn to do that sort of common sense verification. So I am now going to make room for more work here. I'm going to go ahead and change the color to black. So I'm almost done with this problem. I have my force magnitudes, and I just need to compute the forces and then do the addition. So if I do the force that 1 exerts on 3, that's going to be the magnitude that the force 1 exerts on 3 times R13 hat. Now, I didn't write that equation explicitly, but if you think about it, everything pretty much, the formula pretty much matches that, but with the caveat that I got a plus or a minus here. And the plus or the minus depends on if it's an attractive force or repulsive force. And so really that just comes down to, is Q1 times Q3 positive or negative? So what did I have? Well, Q1 times Q3, first of all, was positive. And if I go back, that actual force was 6 times 10 to the negative 5th newtons. So that's the magnitude. Then the direction is in the form of R13 hat, which was just J hat. right? Because that's what we had here. So now I have j hat here. So I know that the force that 1 exerts on 3 is just 6 times 10 to the negative fifth j hat newtons. Okay. Now I get the force that 2 exerts on 3. That's going to be plus or minus the force that 2 exerts on 3's magnitude times r2 3 hat. In this case, the sign is determined by the sign of q2 times q3, which is either positive or negative. In our particular circumstance, that product was negative because q3 was positive and q2 was negative, so their product will be negative. So I go with this, and I end up with minus 3.6 times 10 to the negative fifth times minus 4/5 I hat plus 3/5 j hat. And so we gotta flesh this out a little bit to have a nice answer. So I've got to multiply 3.6 times 4/5 and 3/5. Okay, so first I'm just going to convert these numbers to decimal. So 4/5 is the same as 8/10, so that's just 0.8. 3/5 is the same as 6/10, so that's just 0.6. Oops, okay. So what I'm really computing is going to be force of 2 on 3. It's going to be positive 3.6 times 0.8 I hat, negative 3.6 times 0.6 j hat. And the whole thing will have units of newtons. So if I want to do 3.6 times 0.8, I'm going to go ahead and go to my calculator. .6 times 0.8 is 2.88. So the force that 2 exerts on 3 is going to be positive 2.88 I hat, negative, then if I do 3.6 times 0.6, I think that's going to be 2.43. But let me just double check. 3.6 times 0.6. 216, so I got it wrong. So 2.16. J hat newtons. Okay, so now I have my force that 2 exerts on 3, and I just need to now compute the net force. And I have to give myself an extra page here. So here we go. Okay, so the net force, what is that going to be? Well, the net force, net force is, in fact, let me give myself a little bit more room here. Okay, so the net force is going to be the force that 1 exerts on 3 plus the force that 2 exerts on 3, because the net force is just the total force acting on a particular object. And in this case, we're looking at the net force acting on charge 3. And so, in terms of vectors, the force that 1 exerts on 3 is 6 times 10 to the negative fifth. in the j hat direction. And we're going to add on to that force 2, but I did just notice that my order of magnitudes are off because I dropped my 10 to the negative fifth here. So to fix that, I'm just going to stick the 10 to the negative fifth outside these brackets. Okay, so times 10 to the negative fifth newtons times 10 to the negative fifth newtons. Okay. So I'll have 2.88 times 10 to the negative fifth I hat minus 2.16 times 10 to the negative fifth j hat. This is all newtons. And when I'm adding vectors, you only add like components. So you understand that the j hat goes with the j hat and the I hat goes with the I hat, but they don't mix. So this guy goes with this guy. But there is no I hat component over here, so the I hat here is just going to be left alone. So what am I going to get? I'm going to get 2.88 times 10 to the negative fifth I hat plus 6 times 10 to the negative fifth minus 2.16 times 10 to the negative fifth j hat. All of this is in newtons. So you have 2.88 times 10 to the negative fifth I hat plus, okay, so what is 6 minus 2.16? Well, 6 minus 2 is 4. 4 minus 0.1 would be 3.9. 3.9 minus 0.06 would be 3.84. So this is 3.84 times 10 to the negative fifth j hat. This is in newtons. And this essentially encodes the direction implicitly because it gives me the I hat and the j hat, gives me the components. So I would count this as telling me the direction of the force implicitly. And what do I see here? What I see is the force essentially points up and to the right. Yeah. So we're going to actually work out the angle it points up and to the right at, but it's nice to kind of know that the direction is implied in these components. So I need to compute the magnitude and the direction. The magnitude of the force, the net force, is going to be the square root of 2.88 squared plus 3.84 squared times 10 to the negative fifth newtons. Notice I was able to pull out the 10 to the negative fifth from the Pythagorean theorem. That's something you can always do with an order of magnitude. If you have an overall order of magnitude, then you can just suck it out of the Pythagorean theorem and just deal with the significant figures. So I need 2.88 squared. So once again, I'll go to the calculator. 2.88 times 2.88, 8.2944. So that's this guy right here. Then I need 3.84 squared. Do I keep closing that calculator? I guess I do. Okay, so I have 3.84 times 3.84. What is that? 14.7456. And then we need to add to that the 8.2944. Notice I'm not rounding anything at all because this is just a mathematical step. So I don't want to lose anything by rounding in a mathematical operation. I only want to round when I have my final answer. Okay, so when I add those two numbers, I get 23.04. And I need to take the square root of that. So what is the square root of that? 4.8. So my net force magnitude is going to be 4.8 times 10 to the negative fifth newtons. That's a 10. Now let's go ahead and get the direction as an angle. So by the way, this is part of the final answer. Okay. Now I need to get the direction. Oh, oops. Need to add a new page here. So now I need to get the direction. So to get the direction of the net force, I'm going to go ahead and draw my coordinates. And I'm going to draw the net force as a vector, and I know it points up and to the right. So this is my net force vector. And the net force has an x component and a y component. So I've got the x component and the y component. So the sum of the force in the x direction is 2.88 times 10 to the negative fifth. And the sum of the forces in the y direction is going to be, what was it, 2.16? Oh, 3.84. 3.84 times 10 to the negative fifth newtons. And what I want to determine is this angle here, because I can describe this direction as an angle relative to one of my coordinate axes. So the tangent of my angle is going to be the sum of the force over y divided by the sum of the force over x, because tangent is opposite over adjacent. Sum of the force in the y direction is 3.84 times 10 to the negative fifth newtons. The sum of the forces in the x direction is 2.88 times 10 to the negative fifth newtons. The newtons cancel, the magnitudes cancel, so it just gives me 3.84 over 2.88, which is 1.33. And I'll just put a couple of threes here because, like I said, I'm not going to round on intermediate steps. At least I'm going to try to minimize that. And then theta is tangent inverse of 1.33, because that's how you solve for theta. If you have theta equals tangent of something, you take the tangent inverse of that thing. These are some tangent. And I get 53 degrees, 53.13 degrees. So I've got 53 degrees as my answer. In this class, do try to always stay in degree mode and not radian mode. It's very rare that you're going to run into a situation where you want to be using radians when you're dealing with trigonometric functions. So the direction of my force is 53 degrees, and I could say clockwise or counterclockwise to the positive x-axis. So that defines my angle objectively, that I am talking about 53 degrees relative to the positive x-axis. Okay, and that is this example. This is the direction, and on the previous page we had the magnitude.